standardization. I'm very glad that this talk is after Dr. Moscow's talk, so I do not have to explain why we are doing this. And we probably also do not specifically say whether this is too early or too late. So the outline is that I will give a general introduction, and then I will talk about NIST plan on PQC standardization, and I will talk some challenges and strategies, and we will open for the discussions. So by adding this NIST to my title, I wouldn't worry people do not pay attention about this talk, because I noticed that from this morning until so far, every presentation mentioned the NIST. So why we are doing this? Because quantum computers should completely break widely deployed public key cryptography system like RSA, DSA, and elliptic curve crypto systems. Those are currently specified in the FIPS 186 and the special publication 856A and B. So these kind of basic schemes have been used in many protocols. For example, in the IETF, the TLS talk this morning by Dr. Patterson, and also some other protocols. So we need to prepare for this quantum time, and we need to develop the quantum resistant cryptography. So in my opinion, the too early, that warning from Dr. Rogway this morning is just to tell us don't rush to anything, right? That means the meaning of the do that is still too early. Then, so we are working toward a timeline to have the draft publications in 2023 to 2025. That's kind of many years kind of project. This almost tell the X plus Y should smaller than Z part. And Dr. Moscow already talked about his understanding about Z. So this is about the X, the Y part, X and Y part. So the initial, NIST initial activities, we cannot put this as a high priority research actually before 2012. And I started to have a research opportunity for the NRC postdoc announcement in 2011. Then in 2012, we started bi-weekly post-quantum cryptography seminars. And we also host guest researchers and invited speakers to our seminars. So as this opportunity, I just let everyone know NIST does host international guest researchers, and we also host sabbatical professors, not only in the post-quantum cryptography field, we also do some other fields. So if you are interested in, you can see my posts at the IACR website. And we also participated a lot of research activities and presentations and white paper development with ANSI. And then in the April of 2015, we have our first workshop on the post-quantum cryptography. So we recently published NIST, we call it NIST, actually is in interagency report, number is 8105. about a report about post-quantum cryptography. And then in the PQ Crypto 2016, in February, NIST team gave a presentation, announced NIST initial plan to develop post-quantum cryptography standards. So here is a tentative timeline. So we kind of prepare to release a draft of call for proposals. So before I come to this workshop, we had a meeting with our NIST lawyers. If we put this call for proposals to Federal Register notice, then we need really to get a lawyer's review. So that meeting was a very important milestone in this procedure. We just want to make sure that our lawyers understand what we're doing. So that meeting is that after the meeting I could say, whoa, like that, and then that's really important to us. The fall of the 2016, we depend on how we work on that Federal Register notice. We can have a more formal release for the public for proposals. So in tentative deadline for the submissions will be later 2017. So we have a kind of 3 to 5 year kind of time plan. So we call that analysis stage. And we will have more workshops, and we narrow the selection pool, and we will kind of release reports periodically, and we will release draft standards for public comments. That's what we are planning to do in that 3 to 5 years. So the scope of this NIST PQC standardization, right? So people ask, are you going to standardize group signatures, use lattice? Or are you going to standardize fully homomorphic encryption with the lattice? Well, the answer is no. Currently, the scope is to replace current public key cryptography standards. And in general, it's a digital signature, currently specified in FIPS 186-4, like the RSA, DSA, ECDSA, this is signature standard. And we also kind of, the scope includes encryption used for the key transport, like currently in the special publication 856B, and for RSA, OAEP, and the key encapsulation mechanisms. And we also have the scope for key agreement in the currently specified in special publication 856A. So about the key agreement, I probably add a little bit remarks, because when we talk about the key agreement, people think about Diffie-Hellman, right? Because like the ephemeral Diffie-Hellman can provide perfect forward secrecy, right? So that part, we hope we have that the same thing to replace Diffie-Hellman. However, in some case, it's a one-time public key to do the something like that, and it's not maybe exactly as symmetric as Diffie-Hellman, but still it has perfect forward secrecy properties. That is something we are looking for. And so we separate the encryption and the key agreement. However, they are connected. If we have a very good public key encryption system, and it can generate one-time ephemeral public key for the key transport, that will play the same role. It's just not as symmetric as Diffie-Hellman, right? Not that. Then after I said this, and the question is, are you going to run another computation? So because the AES computation and the SHA-3 computation inspired several generations of cryptographers. We did have fun through that and inspired a lot of research publications, as my colleague John Kelsey said this morning. That is the very, the significance is beyond the select algorithm itself. So when the people ask us, are you going to run a computation? We feel a little bit nervous about that word. Let me tell why, right? So, so first is similar to SHA-3 computation. So we will be an open procedure, and we hope to engage with research communities, implementers, and practitioners, right? So the same way we engage and we open. So we also encourage the public kind of analysis in the submitted algorithm and make the results available. So that's similar as SHA-3. And another way we want to, another way to engage the community, we will hold conferences or workshops for researchers to share analysis and evaluation results. And NIST also release reports periodically and summarize the analysis result and to give the rationale about selections. So if I see these similarities, you say, oh, that is a computation, why you are so nervous to use that word? Well, this is different from SHA-3 computation because the post-quantum cryptography is much more complicated than hash functions. Because for SHA-3, for hash function, and we give the requirement, say, okay, any kind of length message, you can generate the hash value with this many different kind of lengths, and you have to have the pre-image resistance, you have to have the collision resistance, and so on and so forth. So in general, hash function is a much more essential primitive. It's kind of like you can make it a more clean cut in the requirements. However, the post-quantum cryptography is more complicated. And also the algorithms are based on very different mathematical structures and based on the different security assumptions, like some based on the shortest vector in lattice and some based on some other assumptions. So for that, straightforward comparison is almost impossible. And then that aside, I'm not saying that for the AES or SHA-3 candidates, we can make the straightforward comparison, but at least we can compare in some way. But in this kind of post-quantum cryptography, it is harder to make the comparison. Then another kind of point that we want to make is that we the NIST selected the winner. Maybe it's not a winner. Could be multiple winners, even for the same function. For example, for same function signature, we may have more than one kind of winners. And those winners may not be selected in one path, right? It's more or less like our modes of operations to publish all the submissions, but on the other hand, we probably select one at one time. So that is different probably with the SHA-3 computation. So, and also I wanted to have this opportunity to say that we hope this post-quantum cryptography still use existing hash functions in particular like a SHA-2 and SHA-3, unless it's necessary to create some new things, right? So that is what we scope for. And then some more kind of wanted to say that for the SHA-3 computation, if you have followed that computation, it's like we have a larger pool at the very beginning, then we narrow down the first round. Then if it's not, one algorithm is not selected in that round, that's out of the game, right? Then we narrow down again and the final winner. But in this kind of post-quantum cryptography candidates, probably some of the algorithms will not be in and will not be out for a while, and there for the public kind of analysis. And some of the kind of submissions may be merged or received. This we have never done for SHA-3 and AES. So in that case, this is different because if two teams submit something very similar, and then we might want them to merge them and tell us which kind of parameter sites they recommend us. The timeline and some selection criteria may change based on the development in this in the field, because we are still working on we are still conducting research in this area, and it is very possible that we learn something new in the next 5 years. So in that case, we might change something. So that is another significant difference from the SHA-3 computation. So then talk about security, because like SHA-3, we have like say collision resistance at which level, and pre-image resistance at which level. And however, for the post-quantum cryptography, currently we propose to use these two criteria. For encryption, for signature, we cannot try to use existential, unforgeable, chosen message attack, the security concept. And then for the encryption, we propose to use indistinguishable CCA2. So, however, when we give these two security criteria, I want to emphasize that these definitions specify security against attacks which use classical queries, not quantum queries. That for sure is what we propose at this moment. So these security concepts are used to judge the attacks, and the secure proofs are not required for the submission, but however, we consider the security proofs the evidence to support their security claims. So then the question is, you talk a lot about the quantum resistant cryptography, and now you talk all the classical attacks. So shall you consider the quantum security? So at this moment, we consider a few levels. This is the security levels we are looking at. For the classical security, we are looking for 128 bits, 192 bits, and 256 bits. So then for the quantum security level, for the 128 classical security level, we consider two levels of the quantum security level. One is 64 bits, one is 80 bits. Then the people will ask why, right? Why you consider? So, here explained it by some examples. Time over? Okay. So first, the 64 bits is for the exhaustive brute force key search for AES 128. So in that case, if you use Grover algorithm, the quantum secure level is 64 bits. So that is for the symmetrical key. We use that as an example. What we are looking for is a public key system. Then the exhaustive search or brute force may not work at all. So that may work at some stage. Of course, eventually you need to search something, but it depends on which kind of algorithm we are considering and which kind of quantum attack. So we are considering. About the quantum security, I also wanted to say something more. So because this is an area the further research is needed. So we need to, so for example, the question is 2 to the 64 bits, 2 to the 64 of the complexity for the quantum security means what, right? So because we don't have that kind of large-scale quantum computers yet, so we don't know. So we need to scaling up. It's a difficult engineering problem. We do not. We need a more clear picture there. So now it's too early to predict about anything like Moore's law for the quantum device yet, right? We just, Dr. Mosca's presentation talk about the different stages, but we really don't know if there is something similar to Moore's law yet. So we also need some empirical performance of quantum cryptanalysis attacks. For example, running on the classical simulators, and that is a way to estimate. So we also consider the additional factors to consider. For example, like the parallel attack. So here in this slide, you have see some kind of like 128 bits. We have 80 bits. So this one is not based on that quantum attack. It's based on the classical parallelized attack, because the classical parallelized attack can work better than the quantum attack, Grover's attack on the hash function collision search. So that said is that, and so we need a limited but easier to implement model of the computation for the quantum computation. That we will get a better idea about quantum security. So about the quantum security, we really have, in our opinion, still have a long way to go, and we really like to get the attention of the community to make a more effort in that area. So the cost and the performance. So no matter what we are going to select, and this kind of crypto systems will be implemented in the classical platforms. And right now, see, we have diversified applications and diversified the requirements. So maybe for the same function, like a same signature or same, like a in the same signature category, for example, maybe one algorithm cannot satisfy all the requirements. And also we are looking for the algorithms which can allow parallel implementation for the constrained device. Then I will talk about a few kind of issues that we can think about right now. One of it is drop-in replacement. That's on our top list, wish list, right? If we have something, just drop in to the current standard, that will be wonderful. But we have to consider that the current, we know a lot of things are not drop-in replacement yet, right? So, for example, like I mentioned, the Diffie-Hellman key agreement, or you call it Diffie-Hellman key exchange, maybe no exact drop-in replacement yet. And then for signatures, some signature could have very large key, public key, or very large signature yet. And some of the encryption has a kind of error rate. So we need to consider how large the rate of the error probability is something we can accept. So we need to be realistic, right? So if we have the drop-in replacement, that is great. If we don't have, then we need to start to work on the protocol level to look into the impact to the protocols. That is the message I like to convey. Then I would like to talk a little bit about transition and migration, because we received a lot of questions after my colleague's presentation at the PQ Crypto 2016. And because we have the guideline right now, they said that when NIST is going to develop the new guidelines about the security. Well, once we have selected standard algorithms, and once we have a clear idea about quantum security, we will update our guidelines and to give early the guideline as early as possible. So this 131A, 131A is basically say you need to move away from the weak kind of keys or weak algorithms. So this also is something, even we are working on the post-quantum cryptography, but at this moment, if someone really have the weak kind of algorithms there and the weak keys, short keys, you still need to move away from there. About the hybrid mode, and this has been a question for NIST, how to handle the hybrid mode. There are two places the hybrid mode is proposed. One is use the RSA one of the existing public key method, and also a post-quantum method to establish two shares of the secret, right? That's then the final key will be the key derivation from the two shares of the secret. So, for example, one is RSA, one is untrue, or one is Diffie-Hellman, one is transport with the code-based encryption. So, and another signature is to sign the same message twice. One is with existing algorithm, and another one is use like the hash-based signature. So at this moment, NIST really rely on the application to make the decision whether they wanted to do the hybrid mode or not. So for the signature NIST validation program, I mean the FIPS 140 validation program can directly validate the approved portion, that signature. For example, right now we can validate the RSA and the DSA. Then we just ignore another part. Yes, that is how long?
Sorry, I think we're running out of time now.
Okay.
Can you just wrap it up or get to maybe a final point or something?
But for the hybrid mode, we do not consider that the hybrid mode as a summation to the post-quantum cryptography.
Okay.
Then we will work with other standard organizations, and the summary is this is a long journey, and we may not understand everything now. One plan is based on what we know at this point. In a long run, we will learn together with the community and adapt our plan as we learn. So remarks and acknowledgement, stay tuned for our announcement. I'd like to acknowledge our PQC team for their review and comments. And of course, I'm responsible for this presentation. Thank you all for your attention.
Thank you. So I'm afraid we don't have really time for questions, so I would be happy to have you guys ask your questions during the panel discussion that we'll have after the break.
So I will be around for this workshop and also for Eurocrypt.
Yeah,
so if you
I
have
guess...
questions, just ask me anytime. Thank you again.
Thanks.